Hey guys, and welcome to another Tomonometry video. Today we'll be doing a quick introduction to derivatives by their limit definition. So we're going to work through a derivation of the formula, but first I wanted to revisit the slope-intercept formula, which we may have learned in middle school or maybe beginning of high school. And if we remember correctly, it tells us that the slope of this line at every single point is just equal to m. So if we had something like y equals 4x plus 3, then the slope across all points would be 4. But now that we're getting a little more advanced, we start to see lines that look a little something like this, like x cubed. And this is confusing because the slope is not the same at every single point. Take this point and this point, for example. It's clearly steeper over here. So how do we know what the slope of the line is? Well, in order to do that, we can take the slope at a specific point. And the slope of a line at a specific point is called the derivative. And it's denoted as f prime of x. And f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. Okay, so let's try to figure out where our f prime of x formula comes from, because it doesn't really make a whole lot of sense. So what we can do here is take a line f of x, and then take an arbitrary point a with coordinates x and f of x, and then we're going to take another point b with coordinates x plus h and f of x plus h, and naturally they're separated by an x distance of h. Now what we can do with those 2 points is get a secant line in between them, which is just connecting them with a straight line. And this line will tell us the average rate of change between the 2 points. And if we remember correctly, this average rate of change, or the slope of our secant line, could be defined as y2 minus y1 all over x2 minus x1, which, if you remember, is just the slope between 2 points. So how can we rewrite this in terms of what we have over here? Well, we know that y2 is just going to match with this f of x plus h. So we'll call this f of x plus h. And then y1 was our f of x. All over, well, x2 matches with this right here, which is x plus h, minus x1, which was just x. And we see a little cancellation that takes place over here. So then we can just define the slope of our secant line to be f of x plus h minus f of x all over h. However, remember that what we're interested in isn't the average rate of change between our 2 points. We want to know the instantaneous rate of change at a certain point. So let's try to figure out the instantaneous rate of change at point B, for example. Well, the way in which we can do this is by bringing A really close to B to where there is a difference between them of h, but h is basically negligible. So how can we do that? Well, we know that as we bring A closer and closer to B to where they're basically at the same point, h is going to be ridiculously close to 0, but not quite 0. And then our secant line will actually become a tangent line. Since the points are basically at the same place, there's just a tangent line. And then remember that a tangent line is defined as a line that intersects with one point in our f of x, and at that point, they have the exact same rate of change or slope. So that's exactly what we want to do. We want to figure out the slope of our secant line. So how can we do that? Well, I already mentioned that we want to get h to be super small, so that there's basically no difference between a and b. So what we can do is take our earlier formula for the slope of our secant line, but make h super small through a limiting process. So we'll call the slope of our tangent line equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. So now we can just rewrite this as f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. So what we can infer from this is that f prime of x, or the derivative of f of x, is just equal to the tangent line of the original function at a certain point. And by plugging in an x coordinate into this f prime of x, we'll get the slope of our original f of x at that point. Now, if you're interested in a better visual of how we bring our a closer and closer to b so that h is negligible, I'll leave a link in the description that gives a better visual with an animation. So that's it for today's video. Thank you guys so much for watching until the end. So the next part to this video is coming out on June 20th, this Friday, and it's going to be some examples to the formula that we came up with today. Thank you again. Bye-bye.